Good morning. I am presenting our work Dual-Modal Deep Learning with In-Domain Training and Attention for Infant Brain Myelination Prediction. And paper ID is 9578. Authors are Mamilla Harshitha, Mythri, Anju, Bibin, and Varun, Gopi. So as you know, myelination a vital process in brain development where a protective sheath forms around the nerve fibers, improving the high speed of neural signal transmission. And here you can see that there are two set of data from T1 weighted and T2 weighted MRIs of newborn 6-month-old, 12-month-old, 24-month-old and 36-month-old. So we would like to predict the myelination of these brain images. So these are the data distribution shown here. We have totally 710 samples for training and 123 samples for testing. And as the contributions of the model contains T1, T2 modalities, and we have used advanced attention mechanisms such as channel attention, multi-cut attention and cross attention. And we have used density 1-to-1 architecture with the in-domain training. So for in-domain training, we have used adult MRI data from IEEE dataset, and we fine-tuned the DenseNet. Then we have fine-tuned by means of the infant brain MRI dataset. So this model offers an automated and consistent solution for assessing the myelination and identifying the developmental delays and neurological disorders. So this is a structure of the proposed model where you can see that two paths are there, one for T1 images and second for T2 images. And we have attention mechanisms followed by, and finally we have a regression layer. These are the sub-blocks. One is the channel attention block and the other one is the multi-cut attention block. Here the channel attention block recalibrates feature maps by applying global average pooling to capture global context and excitation through fully connected layers to adjust channel importance. And multi-cut attention generates query key and value matrices from the input, calculates the attention score across different regions and combines output from a multiple attention heads to capture spatial dependencies. And cross attention we are using to facilitate interaction between T1 and T2 features by using them as queries, keys and values, enabling cross-model information exchange and fusion for a unified feature representation. And these are the hyperparameters we have obtained using the Keras tuner by giving a set of values and finding the optimum value for the hyperparameters. And these are the result with all the existing network with the attention mechanism. And out of that you can see that DenseNet 1-to-1 performed well. So we chosen the DenseNet 1-to-1 as the backbone, and we have done in-domain training with the IEEE dataset, and then we have fine-tuned it with our brain MRI dataset, that is the infant brain MRI dataset. And when we compare our work with the state-of-art methodology, you can see that we are getting better mean absolute error, Pearson correlation coefficient, coefficient determination, and concordance correlation coefficient. And these are the Bland-Hartmann plot and Violin plot. This Bland-Hartmann plot shows that there is a minimal bias, that is minus 0.11 months with the most data within the 95% limits of agreement. And the Violin plot reveals that the closest alignment between actual and predicted ages are especially from 0 to 20 months, which minimally variability. And the model performs accurately for younger ages, but there are some discrepancies in the older ages from 25 to 36 months. And these are the evaluation studies. We have started the baseline as the DenseNet 1-to-1 in-domain trained model. Then we have different mechanisms we have added, and finally we got the best result for all the combination of baseline plus channel attention plus multi-cut attention plus cross attention. And this is the comparison of computational complexity, and here you can see that the proposed method having only less number of parameters and less memory requirement and total number of flops is higher than MobileNet V2, but still it is performing better. And as a conclusion, we propose a dual input architecture using in-domain trained DenseNet 1-to-1 with advanced attention mechanism, and it achieved good results. And it demonstrated lightweight computational efficiency with only 10.46 million parameters and minimal GPU memory requirement. And our future work involves integrating 3D MRI data and 3D convolutional network to capture and volumetric details and improving the feature extraction and prediction accuracy. And the future work will employ visual explanation techniques such as GradCam or attention heat maps to localize the salient anatomical structures contributing to the prediction. Thank you.